And we actually looked at stationary states of energy. Okay. So, when I say stationary states, of course, it is stationary states of energy, which means solution of H psi equal to E psi, okay, for a time independent problem. So, all the problems that we have done are time independent problems. So, the problems that we actually discussed are, one was particle in a box. Remember, I am not going to go through them, just reminding you what all we did, and all of you know the results of the particle in a box. You get the quantum numbers, which are, and the energy is n square h square by 8 ml square, where L is the box length. Okay. Okay, so this is for 1D box. If you have 2D and 3D box, similarly you will have more and more quantum numbers, and energy will be sum of the x, y, and z, right. So, that you have done, and of course, n is equal to, n starts from 1, 2, 3, etc. And the wave function is, for the 1D box, again wave function is some constant times sin n pi x over n. Okay. So, for 1D box, you can write down the 2D and 3D box trivially by invoking the non-interacting theorem that I stated yesterday. What is the non-interacting theorem? That if your Hamiltonian is sum of 2 operators or 3 operators, wave function is a product. Of course, for electrons they will become antisymmetrized product, that is a different matter, but right now there is only single particle. So, it is just a product of x, y, and z direction. Energy is a sum. So, basically you invoke the same non-interacting theorem and you can generate the total wave function. I hope all of you remember why n cannot be, why n negative is not written and why n equal to 0 is not written. I hope all of you know this. Somebody told me why n equal to 0 is not allowed in the derivation of the particle in a box. Wave function won't be a number, wave function will be 0. No, I did not understand why it is a number means. Number is a proper wave function. Oh, 0 is not just a number. 0 means the wave function does not exist. There is no probability of getting the particle. There is a serious consequence. Number is different. If psi is just constant, it is okay. At least if it is not constant over entire space, then it is not okay, because then it is what is called not normalizable. Okay. So, otherwise it is okay, but it is 0. So, that is not, number is a really incomplete way of saying, giving the answer. Please understand. It is 0 because of course you have a probability, finite probability. Why it is not negative? Because if I take n as a negative, this is nothing but negative of psi n. So, any psi n, if psi n is an eigenfunction, minus psi n is automatically an eigenfunction. So, that we do not have to take, right. So, the point is that if H psi equal to S E psi, then any A psi, H A psi is also an eigenfunction with the same eigenvalue, but that is not a linearly independent eigenfunctions, because it is just a multiplication of a psi. So, any of these will be an eigenfunction. So, we do not take these into account. So, that is the reason negative n is not allowed. Okay, is it clear to everybody? In the solution of this particle in a box, we encountered one important goodness condition, and that was called the continuity of the wave function. So, I want to tell you that there are certain important points that the wave function must satisfy. One was a continuity of wave function, that the wave function must be continuous over entire space. So, that is how we put a 2 boundary condition at the x equal to 0 and x equal to L. Remember, of course, the particle in a box, I have not written the problem that V was infinity outside the box. The potential is infinity outside the box and 0 inside. Of course, if it is not 0, if it is finite, it does not matter, there will be only a scaling. You can easily calculate as long as it is some constant value. If it is not a constant, and that could be an interesting problem. For example, it is infinity here, but inside it is not 0, it is not constant, but let us say it is increasing. So, let us say V equal to x. You understand the problem? Alright. I hope you will be able to solve this problem. I may be entitled, at least for this course, to ask such problems now, okay, without solving them in the quiz at least. So, you should be able to solve such problems. You have actually solved V equal to 0, remember, particle in a box. But now if I put V equal to X, there has to be still a continuity here, remember. So at this point, whatever happens, psi must go back to 0. So you think over it, how to solve such problems. It can be a quadratic function, x square for example, okay. I had also discussed several nuances for this particle in a box, that my coordinate need not be 0 to L, coordinate may be minus L by 2 to plus L by 2, in which case eigenfunctions will be either symmetric or antisymmetric, which was a consequence of the fact that the Hamiltonian is a invariant to parity operator, parity symmetry, which is exactly what I will come to the harmonic oscillator. In fact, now harmonic oscillator has the same problem. So there are several nuances that we talked, and we also looked at 2D and 2D, 3D boxes and their degeneracies, remember. So I just thought I will at least mention you the topic, because I am not again going to cover this, but those who have problem, please revise these topics, that what are the 2D and 3D boxes. They can be a square box, they can be a cubic box, they need not be a square box. I can have a 2D box with L1 and L2 length, then the degeneracies will become completely different, you remember. Then we have to see N1 square divided by L1 square plus N2 square divided by L2 square must be constant. So find out N1 and N2. So those are very interesting problems, but if it's only a problem of arithmetic that you should be able to find out. So I think we discussed many of these problems. Then we also discussed among these stationary states, particle in a box, remember, was discussed very, very elaborately. It's a very, very famous problem. So then the second was harmonic oscillator, simple harmonic oscillator, where the potential was half of kx square. And here in particular, before we solved the problem, we noted that the Hamiltonian itself is even. So minus h of minus x is equal to h of plus x, right? Why? Because kinetic energy is a second derivative operator, d2 dx2. So if you second derivative operator, if you change x to minus x, it remains invariant. If it is d first derivative, it changes sign. I hope that's clear. So d of d minus x is minus d of dx. I hope that everybody understands. So same way, if I do d2 d of minus x square 2, it is same as d2 dx2. In this case, it is plus. Exactly like minus minus becomes plus. So it's exactly the same reason. So the kinetic energy is always an even function, even operator. The potential being an even operator ensures that the Hamiltonian is even, and this is exactly what is called the parity invariant. And we showed, we actually introduced a term called the parity operator. That parity operator P acts on any function phi of x to give you phi of minus x. So that's the definition of the parity operator. And then we showed that this Hamiltonian commutes with the parity operator, and a proof that hence the eigenfunctions, right, are either odd or even. I remind you again, this proof was something that we did quite elaborately. A very similar proof we will do for the permutation symmetry in many electron problem. For boson, that I will actually do. So I am not going to do it again, but it's very easy to show that if H commutes with P, the eigenfunctions of H will be eigenfunctions of P. Then we took the P square psi was equal to lambda square psi. So it's very similar thing that the eigenfunction value of P is either 0 or 1. Very similar thing that we did to show that the psi must be either odd or even. I hope all of you again can prove this, but if you remember, the proof was actually absolutely trivial, that P psi was equal to A psi, then you have P square psi equal to A square psi, and of course P square psi by definition is nothing but psi, right? Because P psi is psi of minus x, P psi is again psi of plus x, so we can say that A square equal to 1, which means A equal to plus minus 1. Very similar. If A equal to plus minus 1, then P psi is nothing but plus minus psi, and P psi is nothing but psi of minus x, right? So psi of minus x is plus minus psi of x. So that was a very 3-line proof that we did. Just again recall that. So the eigenfunctions are either odd or even. Very similar proof will come. Okay, I am again reminding you because it's very easy to forget. So then eventually, of course, we solve the actual harmonic oscillator problem by two means: by ladder operator, remember, and then by actual differential equation solution. And we found that the energy quantum number is n plus half h cross omega, where omega is the oscillator frequency, and n, of course, in this case starts from 0, etc. 0, 1, 2, 3, etc. Importantly, you have to find that since E is n square dependent here, E is linear dependent on n, the spacing between the two are quite different. In this case, they keep on increasing. In this case, it's a constant. All right. Further, in trying to solve this differential equation, we brought in an important concept, and that is called the normalizability. If you remember that the wave function must be such that it must be normalizable. Just like we said continuity of wave function, we said that the normalizability of wave function. So the wave function must be normalizable. So that was another important consideration. If you remember, that is the reason for this. We had pre-multiplied by a factor exponential minus alpha x square by 2, because that ensures that at x equal to plus infinity and minus infinity, it will make it 0. Remember, any wave function, if it does not die at large x, the function is not normalizable. I hope all of you understand this. Huh? So let us take a psi of x, one dimensional, where the limit psi of x at x tends to infinity is finite, which is non-zero. Okay. In such a case, mod psi square dx, if I integrate between minus infinity to plus infinity, either plus or minus, doesn't matter, will become infinity. And if it becomes infinity, it is not normalizable. I hope you understand this. For example, even if psi of x is just a constant across entire minus infinity to plus infinity, some constant k, then do the integration, k square dx, minus infinity to plus infinity, it will become infinity. K square will come out, integral dx is infinity, right? So whenever you have a Cartesian axis which goes up to infinity, that is very important, psi must die. This is not allowed. So in the limit x tends to 0, the psi must die, which essentially means that actually it should become 0. And that is a very important part that you have to. So limit psi x as x tends to plus or minus infinity must become 0. Note that you may ask the question, why did I not use it for particle in a box? I did not, because particle in a box, my potential was infinity. So that automatically ensured that psi is 0. Remember, so that was not required. But if I come here, even if I am talking of this potential, it's not required because the potential here is infinity. It's only up to L, there is no problem. But in the case of the harmonic oscillator, I have to ensure, because the potential is not infinity, potential is just half kx square. So of course at some point it will become infinity, but it is not automatically infinity. So I have to ensure in the process that this has to be 0. And that is the reason the harmonic oscillator psi of x, if you remember, always starts with a prefactor e to the minus alpha x square by 2 and then the polynomial, some polynomial, which also actually has to be cut for the same reason. And that is how the quantization comes. This ensures that x equal to plus infinity or minus infinity, the wave function is 0, because the polynomial is only a finite power of x. This is an infinite power of x square actually. So this will die much faster than its increase. So either way, that will make it 0 in the limit. So that's really the calculus, that whenever you have such a term, it will become 0. X square, because I have to make it 0 on either side. X minus infinity plus infinity, so it must be an even function. This part must be an even function. This polynomial will be either even or odd. So that will make the entire function either even or odd, right, and that is what we have actually seen. So, this is something again, remember we have done it for 1D box, 1D harmonic oscillator, sorry, you can do the same thing for 2D and 3D which are uncoupled, and then your energies will be sum, wave function will be product. If it is uncoupled harmonic oscillator, that is x and y, there is no coupling. You just have a potential which is half kx square plus half ky square plus half kz square. It is trivial to do by using my non-interacting theorem. Okay. So, again that is something that we did, and then the third example that we did was hydrogen atom, which is formally 2 particle, but we said that we can actually convert this into a single particle problem by center of mass and the relative coordinate. So, we transform this into a center of mass and a relative coordinate, right. Center of mass is just the kinetic energy part, the relative coordinate is what we solve, what we call the normally R or R theta phi, 3 dimension, the electron with respect to the nuclei, and we actually solve this problem. It is a very detailed calculation, detailed solution of the differential equation, because it is a 3D problem by definition, which is not coupled of course. So, it is not there x plus y plus z, you have 3 quantum numbers to start with. Like here you have only 1 quantum number, only if you go to 2D and 3D you have 2 and 3 quantum numbers. Here you automatically get 3 quantum numbers and they have been called n, l and m. So, all of you know this is a principal quantum number, it starts from 1, l goes from 0 to n minus 1, m goes from minus l to plus l in steps of 1. I think all of you, hydrogen atom is very well discussed. Once again remember that the continuity condition for phi and theta, and for r, so you actually solve this problem in spherical polar coordinate r theta phi, and note for r which can go to infinity, again you have to use very similar condition like this. So, that is the reason for the radial part which depends on 2 quantum numbers nl, you have a prefactor exponential minus alpha r and then something else. Note that everywhere this prefactor is again there. Here you do not need r square, because r by definition is only 0 to infinity, spherical polar coordinate, not minus infinity to plus infinity. I hope you remember in spherical polar coordinate phi goes from 0 to 2 pi, but r goes from 0 to infinity. Okay. So, I do not need r square, r is sufficient. So, this is again the same effect, the normalizability of the wave function. So, this is basically sometimes this particular thing is called square integrable. That is another name, that the wave function must be square integrable. What is square integrable? That the square of the wave function, modular square of the wave function, if you integrate, you must get a number which is finite and not infinity. I showed you that if this was not there, if I integrate between minus infinity to plus infinity, the number would have become infinity. So, that is not allowed. So, square integrable means square of the function must be integrated in the entire volume to give a result which should be finite. So, in general this should be square integrable. So, we learned 2 important conditions of the wave function which are called the goodness criteria. One is the continuity of the wave function, another is the square integrability of the wave function. We also later in certain cases we have done the problem that not only the wave function must be continuous, but it must be also derivative continuous, which means the derivative of the wave function must be continuous. In certain types of problem this is required. In the particle in a box as it is defined, it is not required, but we have done the step functions. In fact, there is one of the problems that we did again in 4 to 5. I just thought I would remind you. These are all called the goodness criteria of the wave function. No, it is not necessary condition, but these conditions are required only when, see, I mean here if you calculate the derivative here for a sin n pi x, it is a cos x. So, you will get a cos x. So, at cos L, I am not, yeah. So, I am not enforcing that as a condition. I can't enforce because this is a higher level of criteria. So, that is the reason I can't level. If the wave function is not continuous, there is no point talking of derivative continuity. Okay. So, it is not required in that sense. and this is not required because there are no other parameters to be obtained. Okay, so the derivative continuity is often given when there are more parameters in the wave function and you have less equations. So that also comes up as a conditions to get those parameters. That's correct. I am saying the wave function is 0. That part is right. So I am saying that since if you want to make a continuity wave function, then I can't impose the derivative continuity. So this is a higher criteria. Okay, so that is the point. If I have already satisfied this, then I will see. Remember, these are all goodness criteria, which is called the desirable part of the wave function. Even you can have wave functions which are not square integrable. There is nothing wrong in that, except that we don't like to work with that because I can't define my probability. So most of these criteria are not necessary conditions. They are goodness criteria. So they are very often called the goodness criteria of the wave function. So the wave function is well behaved. There is another term which is called good behavior of the wave function. Okay. So in this case I can't do for a simple reason because that will clash with my continuity. And continuity wave function is a very important conceptual criteria because that means you are saying that the density abruptly changes, probability density, which is non-intuitive, counterintuitive I would say. So that is the reason it is very important to have this.